Hi everyone, my name is Karthik and this is my submission for the Grabon AI Labs Assessment 3, the GARD. So what I've built here is not just a collection of testing scripts but a fully automated statistically rigorous evaluation pipeline. So the goal of this architecture is to treat LLMs as a production software. So manually wipe checks don't scale. So I designed a system that acts as a deterministic gatekeeper. It prevents prompt regressions and model drift from ever reaching production. So before I run the pipeline, let me walk through the core architecture and the key modules. So first is a centralized LLM gateway. So instead of having every evaluation script manage its own API calls, I routed all the traffic from all LLMs. So I've used four here: GPT-4o Mini, Claude, and Gemini, and Llama models using Grok. So I've used all of these models and routed both the generation tasks and also the LLM as a just judge tasks through single LLM runner Pi module. So all the traffic goes through this module, and this is responsible for handling failure cases here. And this decoupled my evaluation logic from my network infrastructure, and it allows the system to enforce global exponential backoff, handle multi-provider routing across Grok, Anthropic, and Gemini, and also track token costs through down to the exact fraction of a cent across the entire pipeline. The next architectural modification that I've made here is the eval file. So this is one source of truth for all the evaluation that are being done. So I'm given three tasks to perform: deal copy, insurance intent, and credit narrative. So I've created fake data sets for each of them, 30 each, uh, and define the metrics that they need to be evaluated on. So if you really want to add or remove metrics, so we could just modify the YAML file and run the file as usual. So this file goes into the universal run evals.py file, and uh, yeah, the YAML file parses through this and runs all the evals for all the datasets. So let's look at the setup here. So uh, the default model is GPT-4o Mini. So like this is used for each of the tasks and their prompts. So this is the input template of the prompt, and what each of the agents or each of the prompts for each of the datasets should do, like, is given by the system prompts that I've made here. So this one's for the insurance agent, and this is underwriter agent. And yeah, let's run with this setup. So some things about the setup. So the deal copy uses Anthropic's Claude, and I've also added a feature to add judge models. So uh, yeah, we could also add judge models. So here we use GPT-4o Mini, and yeah, for insurance intent we use Gemini, and yeah, for the credit narrative we use like Grok's Llama. So yeah, let's start running it. Yeah, so as we can see, the deal copy is being evaluated, and it's being run. It would take a while, so like I'll skip this part for a few minutes. So yeah, it has been a while. So like the deal copy part is done, and like the cost it incurred is yeah, $0.0039, and after that, like the insurance intent part is running. So GPT 2.5 Flash is currently giving an API error. So like this is uh, yeah the fallback case, and like what it does is it falls back to GPT-4o Mini, like, which is more stable in my test. So uh, yeah, so it runs GPT-4o Mini, and like it gave us a cost of 0.0023. So now let's evaluate credit narrative. So this will take a while because it uses an LLM as a judge model. So yeah, I'll let you know once this part is done too. So yeah, the run was done, and like 90 cases evaluated. So I've created a data set of 30 cases for each of them, and like 90 cases were evaluated for all of them. And yeah, the format compliance score was not so good for yeah, using the haiku model, and like the semantic similarity is pretty good and persuasiveness is pretty good too. Uh, yeah, we could also see like by how much uh, the baseline model has changed. So like the format compliance score, like it's for deals, and we could also see like which deals have regressed, and also their latencies. Since it's just the first commit, so we only see one commit here, and like no, uh, yeah, no prompt diffs, and the history just adds is just it adds as a single entity. So now let's look at a failure case. So here I've changed the deal creation part. Uh, I've changed the prompt here, so it's more aggressive. So this is ought to trip the semantic similarity case, because it's what is evaluating deal cases. So uh, yeah, I've already run this case for like almost 90 cases. So this is how it looks like. So 90 cases are evaluated here, and the pipeline cost is slightly higher than before. The intent accuracy before was 31%, but like now it's gone up to 36%, so it has improved. So the change I made here is, we can see in the diff here, this is the baseline score. It doesn't have any commits here, but if we look at the new commit, yeah, I've added a much stronger model here, like 70 billion versatile model. Uh, and tested it with 90 cases, and here we can see like which deals have regressed, and which and even in other data sets, like for scores like factual grounding, these are some scores that have regressed. You can also see which deals have regressed, and like which intents have passed, so we can go through the whole CSV file. I'll paste this during the submission. So let me do a quick rundown of the whole architecture right now. So yeah, firstly, the GitHub Actions, and we could perform it's the same using our pipeline using GitHub Actions, and like I've configured the eval config YAML file. So this is the pipeline YAML file which runs our test cases, and yeah, I've created data sets using Gemini, and I've created 30 each for all of them, and yeah, so like the Git portal triggers PR, and like our evals run here, and when they're running, so there are two cases here. So like the evals run per task, and like also like for as a judge model within the individual metrics. So the LLM gateway router, so I built a router here which routes to each of the models. So like the fallback model for all of them like is the OpenAI model, because it's much more reliant, and uh, yeah, we could configure uh, all of our evaluations in the eval config.yaml, and yeah, for the GitHub Actions, like we built a pipeline, and like in a separate YAML file we built a pipeline uh, which runs the file. So the next part is a metrics registry. Like here we put in all of our metrics and wrap them so that they are compatible with the YAML file that we pass in, and yeah, we define it makes it easier to add new metrics. So like this, I could show it in the next technical round interview, where I could add the new metric much faster using this architecture, and yeah, I've split the metrics into two parts: deterministic metrics and LLM as a judge metric. So like there are two of the two metrics in this assignment, and yeah. So after that, like once these metrics are evaluated, so like the statistical engine runs, which decides which commits to merge and which to not merge, and yeah, all of the commits information is stored inside history.json file, and like this is useful to see how much has our baseline improved from the previous uh, from the previous run. So yeah, we can then so first is a centralized LLM gateway. So instead of having every evaluation script manage its own API calls, I routed all the traffic from all LLMs So I've used four here: GPT-4o Mini, Claude, Gemini, and Llama models using Grok. So I've used all of these models and routed both the generation tasks and also the LLM as a just judge tasks through single LLM runner Pi module. So all the traffic goes through this module, and this is responsible for handling failure cases here. And this decoupled my evaluation logic from my network infrastructure, and it allows the system to enforce global exponential backoff, handle multi-provider routing across Grok, Anthropic, and Gemini, and also track token costs through down to the exact fraction of a cent across the entire pipeline. Going to the statistical engine, so I'm moving beyond simple percentages here. So uh, yeah, I've used the McNamee test for binary metrics. So uh, yeah, McNamee test is usually used for binary metrics, and it gives us a clean p-value, and like also helps us get the regressions. But for continuous metrics, we use the bootstrap test. So what bootstrap test does is it takes in a lot of it takes in our array of outputs like which are continuous. It multiplies them, it makes them into a matrix, multiplies them, and like averages them across uh, across their length, and we get like almost 10,000 samples here if you're using 10,000 limit, and it sorts them based on their scores. So if it's negative, it's more to the left, and if it's positive, it's more to the right, and we trim each of them to the left and right, and yeah, in that case we get the interval for the paid bootstrap test. So the go and no go and inclusive parts come from the confidence interval for continuous metrics, and for we use p value for binary metrics, and p value that comes from the McNamee test, and like for this bootstrap test, it is confidence interval. Yeah, we can then evaluate using we can then evaluate for both continuous and also discrete metrics. For discrete metrics, we use McNamee's test, and for continuous one. So this is one of the most successful cases that I've done using it. So even this uses uh, 5 values because I wanted to show how it works. And this is the first case, which is always successful because it's the baseline score. Uh, yeah. So like once we push into the Git repo, so it runs an evaluation. It runs an evaluation process, and this could be better explained by the eval YAML file. So eval get YAML file. So yeah, firstly it pulls the config file, which has all the information about which models to run and which tasks to run, and yeah, it then starts to install all the dependencies and set all the permissions here, and uh, also like in the setup steps in my readme I'll mention how we could set up Anthropic and all of these API keys yeah, for running within the Git interface, and yeah, finally it runs the eval file, and this takes around 15 minutes if you run it using Git and using all the 30 evaluation metrics, and uh, yeah, and finally I've used artifacts to save the history and like also to save the eval report. So uh, the ideal scenario would be the history would be saved in our backend databases, and like we could import that history, and like we could compare now if compare regressions, and also like I've put in the artifacts the eval report raw.csv, which we could extract using Git. And for now, like what I did was we could use Git to grab the history from the Git interface and like put it in our repo, and like then push it again, and so that we could dynamically add history as the commits go on, and like we could have a good history of the commits that happened before, and their timestamps too. So this is basically the architecture, the overall architecture, and yeah, I believe this. To wrap this up, this architecture provides complete and deterministic observability for agentic workflows. So It provides exactly how much an evaluation costs, how long it takes, and statistically guarantees whether a change is safe to merge. If I had 2 more weeks to iterate on this, my first priority would be wrapping up the LLM gateway in async.io. So running these 90 cases synchronously takes about 45 seconds. With async chunking, that could drop down to around 5 seconds. So secondly, I would set up a shadow testing harness to replace the expensive GPT-4o judges with a local model, a fine-tuned one, an open source model to drastically reduce the valuation and compute budget. Thanks for your time, and I look forward to discussing this architecture further in the technical deep dive.